Welcome to the course and workshop, How to Teach Science and Engineering. Please go through the previous lessons. In this lesson, lesson 5, I'll explain the steps to teach engineering through a sample lecture. My name is Sinha, Dr. Ranbir Sinha. I work for the company Sinha Research, Switzerland. Teaching science and engineering is different from teaching, for example, history or literature, because the students need to apply their knowledge to create something, some engineering product, or solve some engineering problem. So they need to understand the concepts, need to learn the process of analyzing a problem, finding solutions, verifying it, and producing something useful. I'll include certain points if you're planning to teach online. I'll include some points regarding that. Preparation. You should spend about 25 to 30 hours preparing for 1 hour lecture. Okay? Either in class or online lecture, you need about 25 to 30. If you are very experienced, maybe you can reduce it to 15 hours. First thing to do is to divide the course. Suppose you are planning to teach certain things in electrical engineering. Divide the course into topics and select the right topics. It's almost impossible to cover everything that's written in the textbooks. So you have to choose the topics that are most interesting and most fundamental that the students must learn from you. The rest of the things you can leave it to the students. Once you have explained the basic concepts, and if they can solve some problems, they can pick up the rest on their own. Okay? So it's important to select the right topics, interesting topics, useful topics. The most useful concepts must be clarified to them in class. Choose appropriate resources, tools, video animations, and hardware props. There are hundreds and hundreds of resources available, books, videos, YouTube videos. There's no way you can include all of them. Most of them are not very useful anyway. So you select the best resources, okay? Maybe a very good textbook, and maybe a few related videos. Tools, basically a blackboard, chalk, and few pieces of hardware should suffice. Rest of the things can be done in the lab classes, okay? But if you're teaching online, certainly there are certain tools you need to learn first. Videos and animations, students like that. Now you have the technology, so show some videos and animations to make the concepts absolutely clear to the students and also make them interested in learning. Okay? I'll give you an example of all of these through the sample lecture today. Hardware. Suppose you are teaching something about electronics, bring a piece of hardware. Sometimes it's not possible, but if you can bring it and show certain components that we are going to learn the theory about this today. As I always say, product first, theory later. That makes them interested in the class, okay? You can bring some simple props for yourself, okay? Hardware, whenever possible, bring it. If not possible, for example, if you are teaching about gas turbine, of course you cannot bring a gas turbine there. So bring some videos and animations of gas turbine, okay, in the class. Learn the existing online teaching system. There are lots of teaching tools. For example, right now I'm using PowerPoint. You can use some other tool too. Now to record the video, I'm using OBS Studio, okay, and simple webcam. Keep it simple, but learn it very well. System or platform, and make the best use of it. Unless you know how to use the tools, it's going to be very difficult to produce a quality product, teaching product. Imagine you are planning to teach one average student. This is something you should prepare in your mind as if you are teaching an average student, trying to make the concepts clear to an average student, make him very productive engineer finally. Okay, it should feel like a private tutor is guiding a student. Okay, online, exactly the same thing. You have to focus on one average student. Keep that in mind. Contents is extremely important. Contents are more important than all the tools and everything else that I mentioned earlier. Make two versions of the contents. For example, if you are making this sort of presentation using slides, make two versions. One detailed version where you write down the objective, outline. I'll give you a sample outline, the next page. Fill in the details with texts that you are planning to say. Pictures, use more pictures than text. Following my earlier lessons, I have 4 other videos. Please go through them. This detailed version is for you. Whatever you're planning to mention, whatever you are supposed to know, the questions, answers, everything should be included in this. Then make a shorter version of that you're planning to present to the students. For example, what I'm presenting now is a shorter version. Make a shorter version that will be presented online, or you're planning to show it during your lecture. So remove not so important texts, data, etc., because you're limited by time, right? Also, you don't want to bore the students with all the details on the notes. You can speak certain things that don't need to be on the slides. Okay. Follow the instructions and suggestions given in the earlier lessons. Okay. So because this is a long lecture, I'm going to speed up. You may have to go through this video twice and make your own notes. Rehearse a few times and record to check the flow of information. This is very important. Flow of information. Once you record your own video and go through that, for example, I recorded this video 3 times. I found mistakes, and sometimes the flow of information, I was forgetting to mention certain things, and it seemed like it was not a smooth flow of information. Suppose you're starting your teaching career, and I'm teaching you something. There were some gaps. I tried to fill them in the next video. Okay. Flow of information. Build the information from what the students know to where they are supposed to go. In between this, smoothly feed the information they need. Timing. Quite often I overshoot 1 hour time that's assigned to me. So you have to practice to reduce the contents so that you don't sound repetitive and you can save on time. And improve the contents of version 2 and finalize it, version 2 that you're planning to present. Okay. Implement. Finally, you have to implement that. Do the online teaching or in-class teaching and record it, video record it. Evaluate yourself, assess yourself from the video, watch your own video. You'll find some mistakes and you can think, I could probably improve that. I'm repeating something too many times. Most important things must be repeated a few times so that it really gets into the head of the students. Okay. But unnecessary things do not repeat. Try to cut down on that. Feedback received. That's just an example. There may be other kinds of feedback too from the students. For example, some students may say, you're speaking too fast, then slow down. Some people may say, you're making it too complicated, then simplify it. Take only the most useful criticisms and improve. Finally, your objective must be met. For example, my objective in this presentation is a new teacher of science and engineering, let's say a lecturer or assistant professor, should learn how to teach engineering. And at the end of this course, he or she should have a good idea what steps to follow. What steps to follow to make her teaching excellent and effective. That's my objective. So I've written that down. Okay. All right. There's something from Albert Einstein. Please read that. Perfection of means and confusion of goals seem, in my opinion, to characterize our age. What does that mean? We are focusing too much on improving these tools, but the contents and the goals are getting confusing. So your goals must be met. So you have to be absolutely clear about what is your objective. Well, what's the objective of your teaching this class? Okay. So tools are important. Tools and means are important, but not as important as the goals. So please do not sacrifice your goal and the contents because of the fancy tools. All right. A sample class in engineering. Today, I'll give you a demo of how I teach, why the students understand what I teach and can apply them. And also I'll explain the details of why I'm teaching in a particular way so that you can copy some of the points, some of the most important points. Introduction. We're going to talk about engineering vibrations today. Okay, so I have to tell them what is vibration, why study it. That's the first thing they should know. Very vague idea about what vibration is, what they expect from this course, and why study it. That's very important. Why? Where is it going to be applied? What kind of problems they can solve using that? What new things they can create if they study vibrations. So objective of studying vibrations should be very clear in their mind. Very clear in the sense, not the details, but simple things like if I study vibrations, I can solve this sort of problem and I can create these kind of new products. Okay, so let me introduce a video here right away. This is from NASA Langley Research Center. This is about flutter, vibration caused by airflow. This is a bridge, Tacoma Bridge in Washington. It's 1940s. Almost new bridge. Look what happens. Shaking. That's vibration. It broke and fell apart. This is wind tunnel test. Vibration caused by airflow. It's a model aircraft. Wing broke. It's the tailplane. It's a fighter plane. It's a model aircraft in a wind tunnel. Airflow over aerofoil. It's also a rocket or missile. This is a real glider. See how it's vibrating. This is a model of a rocket. This is a real model in a wind tunnel. They're all vibrations, but special kind of vibration called flutter, caused by airflow. The tailplane. It's a real aircraft. Broke, fell apart. This large plane is getting unstable. Trying to control. Good. You have seen enough. So you got some idea about what vibration is, how dangerous it can be. A bridge fell apart, right? Almost brand new bridge. Very well designed, but they forgot to take care of something called vibration in the design. All right. So what's the use of vibration? You saw some of the bad things vibrations can do. Is there any use? Yes. Musical instruments work on the principle of vibrations. So if you study vibrations, you can create musical instruments. At least you'll understand how they work. Okay? Headphones. Here's a pair of headphones. Electrical signal come here, and there's a diaphragm that vibrates in a particular way. That creates music for me. Or I can hear the sound, understand it. Microphones is exactly the opposite. Whatever I'm speaking, that sound wave creates vibration in some diaphragm that gets transferred into electrical signal. Then you can process it. You can amplify, for example, make it louder, remove the noise, make it sound better, etc. Okay, it's all vibration. Vibrating sieve. Suppose in a company, manufacturing company, you want to separate large particles from the small particles. You can use vibrating sieve. I want you teachers to find some video related to that and give a demo to the students. Okay, they'll know how to use principles of vibrations for some useful purposes. Okay, there are many such uses. Also, vibration can be a problem. If you do not study it, you will not be able to solve these problems. Cars, for example, cars have a lot of vibrations. Engine creates vibrations. Driving over the road, rough road, that creates vibration and noise. So that's why we use things like suspension. Engineering cars have suspensions, so the ride is comfortable. Unless you know how to study vibration, how to take care of it, you will not be able to design that. Trains have noise and vibration. Sometimes it can vibrate so much you can fall off the track. Planes you have already seen. Bridges you have seen. Vibrate and create a lot of problems. Machines, most of the machines do move at a fast speed, causes vibrations. Robots, just to give you a simple example, suppose that's a robot arm that's supposed to put electronic components on a motherboard. Okay, if it vibrates and you don't know how to control it, how to design the robot arm and how to control it, it'll put the wrong components in the wrong places. It's not going to work. The entire effort is going to be useless. The product will not function. So you need to study vibration. You need to know how to control the vibration. So what are the problems? Major problems created by vibrations, noise, poor performance, and failures, etc. Okay, so now you know how important vibration is. Everywhere you see around, anything that moves probably has some vibrations. You need to study and design it properly. So, introduction is one of the most important part of the outline. That has to be so good that students get excited. They know why they are going to study this. Okay, please include that in every lecture. Then approach of the study. We'll take something simple to explain vibrations and then make it more complicated later on. The fundamental principles must be very simple and clearly explained to the students using some simple thing. We'll take simple harmonic motion. You have to explain what simple harmonic motion means at some point to the students. We'll take a very simple case, a model that's called mass spring. If you can bring a piece of hardware, find a spring from your physics lab or from the workshop and a mass, that would be ideal. Hang the spring, then hang the mass and do the experiment with it. If not possible at all, then draw on the blackboard. You should do that anyway, or on a PC. But hardware plus this would be the ideal combination. For example, here I have just drawn a picture. There's a spring, here is a fixed support. I'm hanging it from there. I take a spring, okay, then I take a mass, hang it there and hold it and slowly lower it, and then at some point it stops coming down, then I gradually remove my hand. Okay, so that's my spring mass system. The stiffness of the spring is K. Okay, spring constant or stiffness is K. And here is a mass that's hanging from there. Pull the mass and release it and ask what will it do and why. Suppose I pull the mass by about 5 centimeters. If I release it, what will happen? Ask the students. Do not do it first. First, ask them hypothetical question. If I pulled it by 5 centimeters and released it, many of the students can imagine, and that's very important for engineers. They should be able to visualize without actually seeing what's going to happen based on their past experience. Okay? What will happen? Some of the students will say it will bounce back. Some will be more specific. They'll say it'll bounce up, then come down again, and bounce up, come down again, like that. Some students may actually use the term it's going to vibrate up and down. That's wonderful. Different ways of explaining the same phenomenon. This is exactly what it'll do when you release it. They'll be excited that, yes, we were right. Okay, this is what it does. Why does it do it? This is what happens. When I pull it, spring gets stretched, and spring tries to pull the mass back. There's a force on it. So when I release my hand, that force of the spring on the body tries to move it up. But then by the time it comes to this neutral position, I'll call it neutral position or reference position, this mass has gained some velocity. It's got some momentum, so it continues to go up because of Newton's first law of motion. Then the spring gets compressed, and spring tries to push it down. And after some time, it moves to a point. By the time it's slowed down to zero speed, but spring is compressed and it's pushing it down, so it comes down again. So that's what happens. Okay, so that's one of the easiest way to demonstrate vibration. All right, what do we want to find out? In your outline, you have to be absolutely clear. We are studying this, but what do we want to find out? What do we want to analyze? What do we want to know about this phenomenon, vibration? What do we want to find out? Okay, then formulate the problem, introduce the technical terms necessary to describe, for example, vibration, spring constant, mass spring, amplitude, frequency, time period, okay, all that, sinusoidal, all these terms you have to introduce. So I'm showing the outline. I'll go into the details later how I do it. Explain the approach. Once you formulate the problem and introduce certain technical terms, you'd have to introduce the technical terms gradually as you go through the explanation. But approach, you have to explain. Before you start deriving the formulas, how are we going to solve this problem? Ask them. How are you going to? First, what do we want to find out? You have to explain. Formulate the problem. Only the first few steps. What we want to do. Then explain the approach. How are you going to find these things out? How are you going to solve this problem? Okay, make them think. Please make them think. Do not spoon feed them with all the things that you know. Ask them the questions. That will make them very good engineers later on. Okay. Then derive the formulas using physical thinking, drawing, and mathematics, all three. Do not start deriving only using mathematics. Everything in engineering is related to some physical things. That's the difference between mathematicians and engineers. Engineers need to use mathematics as tools to solve some real problems. Okay? So everything should relate to something physical. Okay. Please write that down. That should go in your outline, and then details will come. All right. Let the students calculate the frequency, period, etc. Whatever comes out of the formula. Let them calculate it in the class. Okay? Otherwise, they'll just listen to you and understand only 50% of it. They'll not know the details. They'll not know how to apply it. So your teaching is going to be 50% successful. That's not good enough. Okay? So you have to make them do some simple work right there in the class, then assign more complicated problems as homework. Do an experiment and show if the formula works. If you can do that, if you actually brought the hardware and let it swing, take a video of that once a month, okay? And then somehow at the end, once they have calculated something, those results match with the measured from the actual experiment using video, for example. If they match, students are going to be really happy. They'll be convinced that theory works. Okay, so it's very important. It's not probably always possible. Try to include some experiment right there. Experiment You can introduce this as a lab class. The lab class should reflect whatever you are teaching as theory. They should correspond at least, okay? In the experiment, probably you'll not get time in the lecture class, but in the lab class, you can ask them to vary the amplitude, mass, amplitude. Probably you can vary right there. Just pull it a little bit longer. Okay, mass. Use 2 springs in parallel if possible to make it stiffer, and ask them to repeat that, calculate, and see the calculation matches with the experiment. Okay, so that the entire concept, the analysis process, the formulas, everything gets absolutely clear in their mind, and they can apply them to solve more complex problems. Ask the students to derive the formula for velocity and Vmax. Don't do all the details of everything for them. Derive the formula, for example, for position. So how are you going to find the velocity from there? They should be able to tell. Take the first derivative, let them do it. Let them derive the formula, okay? And then find out the maximum value possible for that. Give hints about approximations, damping, etc., which you could introduce in probably in future classes, damping, damped vibrations, etc. I'm just giving an example. Whatever topic you choose, there will be similar steps. Okay? Introduce and tell them what approximation. Okay, what approximation do you think I should introduce here? I'm ignoring the mass of the spring. Okay, otherwise it gets complicated. It's possible to introduce. That will be very, very complicated for first-year engineering, second-year engineering classes. Okay, so I'm ignoring the mass of that one, thinking it's very, very light compared to this mass, so I'm going to ignore that one. What else? The real experiment that they see, it vibrates, and after some time becomes stationary, doesn't vibrate anymore. Here in theory, it's continuously vibrating. What's the difference? Let them think about that. You could throw in the term damping, viscous damping, because the air, maybe there is some energy loss because spring is being stretched and compressed. Some energy is being lost, and also because air friction, which is viscous damping by the air, we are ignoring it. If I did that in vacuum, probably it will run for a longer time. All right, because damped vibration you'll teach probably in the next class, a couple of classes later. Okay, vibration, oscillation, simple harmonic motion, periodic motion, so many terms. Are there differences? There may be minor differences. They should know. Oscillation, for example, some pendulum oscillates, but that's not vibration, is it? It's not. That's simple harmonic motion. That's true, but it's not vibration. Periodic motion doesn't have to be simple harmonic motion. Periodic motion, anything that repeats, that's a periodic motion too. That's periodic motion too. It's repeating. Okay? So, but that's not simple harmonic motion. So, explain the terms and ask them to find out the slight differences. You can explain one or two and ask them to do. Leave them to do the details, a lot of work. That will make it clear in their mind. Okay. Cause of vibration. This is something finally they have to go back home with at least one thing absolutely clear in their mind, something short that they will remember. You have to put that in the conclusion somehow. They should be convinced that main cause of vibration is, of course, some kind of displacement or force, and the system must have an elastic restoring force proportional to the displacement in the opposite direction of the displacement. Spring is trying to pull it back. I stretch it there, spring tries to pull it back. If I push it, the spring is trying to push it back. An elastic restoring force, trying to bring it back to the original position, neutral position. That must be proportional to the displacement. It doesn't have to be linearly proportional, but those are details, okay? With a negative sign, opposite to the displacement. That will cause vibration. Some displacement or external force, and the system should have a restoring force proportional to the displacement. That will cause vibration. At least that part they must have in their mind, so that in future, if they're working for industry or trying to solve some vibration problem, they should be able to recognize that this is not a vibration problem, this is some other kind of motion because there's no elastic force involved. Or, yes, that looks like vibration problem. I'll use all the theories I have learned to solve that problem. That's very important to recognize the problems. Many people, even with degrees, do not recognize the problem. That's the problem, okay? All right. Sounds funny, but that's how it is. Demo with a real experiment, okay? So these are the basic steps. Demo with a real experiment. Take a video, okay? You show the hardware, make it move, pull it down, let it go down. Take a cell phone, take a smartphone, take the video of that. From that video, you can see a lot of things. You can see the displacement by pausing the video. You can see, you can measure the time. How much time did it take to make 10 cycles? Okay. From that, you can calculate the frequency. Later on, when you do the modeling, mathematical modeling, that calculation matches with what your video has captured. Students will be excited that yes, professor knows what he's talking about, he or she. All right, a sample class in engineering, vibrations. So what are the things you need to do? Objective. What is your objective? We want to find the position and velocity of the body as a function of time. How are you going to tell them that? This is what we are going to do. Okay, something is moving up and down. What do we want to find out? It's some kind of motion. If we can find out the position of this with time, the major part of the problem is solved. We understand now how to model it. Okay? Once you know the position, you can find other things. So anytime there's some kind of motion, most likely the objective is going to be to find the position with respect to time. Position of this body in this example. You can take the derivative to find velocity, acceleration, etc. and the forces you can calculate at any time. How the force varies with time, you can calculate all kinds of things you can do. That's the main objective we want to find. So anytime there's a dynamics problem, they know probably the main objective is going to be to find position with respect to time. You can explain the difference between kinematics and dynamics. In dynamics, you apply force and check the motion. In kinematics, motion is given, you try to find what force can cause it. Okay. Approach. How are you going to approach that? That has to be explained very well. We can write down the equation of motion and solve the position as a function of time. This is a standard approach. They should know that it's a dynamics problem. We have to write down the equations of motion and solve it. There may be more than one equation, so solve them for position as a function of time. That's usually the main approach to solving dynamics problems. Derive. We have to derive that. First, do this. Draw a very simple sketch. Okay, this is the representation of spring. This is the fixed support. It's hanging from there. And there's the body simplified. Don't make the pictures too complicated. Make it simple. Okay, and because I have slowly released it till it stops, then remove my hand. So that's the neutral position because the weight of the body, it has stretched the spring till the spring force becomes equal to the weight of that body, mass times g. That I'll consider as my reference, x equals 0, and x positive I'll take in this direction. Downwards, x positive, I'm free to choose. I could choose upwards too. Okay. Reference I have chosen at the neutral or equilibrium position. Good. Now draw a free body diagram. You say, if I stretch it up to here, give a displacement of x, then I draw the same body. Instead of the spring, I replace that with a force. That's free body diagram. Body with all the forces on it, represented by arrows, forces, moments, etc. That's free body diagram. Okay. Now I'm going to axis system is downwards positive. I have taken, and this is my reference point. So there's a distance x here. It's a generic x, some x variable. At any x, this is going to be valid. Okay. So introduce these terms, free body diagram, reference, equilibrium, these terms, and say, now we're going to analyze just this body. This body is free, it's got a force on it. I'm going to write down the equation of motion on that one. Okay, suppose the body is at a distance x from the neutral position. How much is the spring force? How much is this F? See, that's the property of the spring. Spring stretched by x distance creates a force, this linear spring, K times X. K is the spring constant or stiffness of the spring. Okay. But in the opposite direction, if the displacement in this direction, force is in that direction, so I have to put a minus sign. F equals Kx with a minus sign. Extremely important. Signs. Many students get confused about the signs, whether to put that way, should I put the arrow that way? If I put the force in the same direction, x, do I need to give minus? All these things are very important in drawing free body diagram. Believe me, hundreds of students make mistakes because we don't clarify it properly. So go into the details of drawing free body diagram, okay? So that's one relation we got. Now, generally, to solve dynamics problems, we use Newton's second law of motion, all right? So this is a general approach. They should know what are the general steps they should follow to solve any dynamics problem. F equals mass times acceleration. That's the Newton's second law of motion, okay? There are some other formulations. You don't need to get into that now. Your Hamiltonian formulation, etc. Okay, Lagrange's formulation, but let's stay with Newton's second law of motion. Mass times acceleration. Acceleration is simply the second derivative of position. First derivative gives the velocity. Second derivative gives the acceleration. With respect to time, d squared x dt squared, okay? And there's a shorthand notation. X double dot means the same thing. D squared x dt squared is x double dot, time derivative, second derivative, mass times. So I have now the equation, one equation here, another one. I move this one to that side. Mx double dot becomes f. F I substitute here, minus kx. From there I can bring the m down here, divide both sides by m. X double dot equals minus k over m x. That's my equation of motion. Okay, that equation describes the motion of this one, but it's a second order differential equation. Okay, because I have second derivative, and this one, same thing as displacement. I want to find this one in terms of time, so just derivative is not enough. So I have to solve this differential equation, second order differential equation. What function x, as a function of time, will satisfy this equation? That will be my solution. Then pause, let them think. You said too many things. This differential equation describes the motion of this mass spring system, or specifically of this mass, which is a second order differential equation with respect to time. It involves second order derivative. It could have had first order derivative to x dot, but this one doesn't have that. And x itself, x the displacement. What we want to find is x as a function of time. Okay, what function x would satisfy this equation? That's what we want to find. So, okay, can you guess what function x would satisfy this equation? Well, let's take two different approaches. Physics, they have seen how it behaves. What kind of function could be describing this motion? And then we'll do mathematical approach. We'll take mathematical approach too. Okay. Now think what kind of function may give the solution to this differential equation. Two approaches, physics and mathematics. You have to actually always relate physics and mathematics together. Okay, so let's say physics part. How was this motion From neutral, it was going down, up, down, up, down, up. So it's maybe a function like this, right? With respect to time, some time is going up, sometimes going down, up, down, up, down. This could be a possible solution, okay? That's an initial guess. It could also be something like that. Squared kind of goes up, then stays there, then comes down, stays there, then goes up with respect to time. This is very important. I'm plotting time in this axis, displacement in this axis, okay? But ask them the details. So do you think this is correct solution? Some of them will think and say, no, this one would be just going up and immediately coming down like that with constant speed, because the first derivative of this one is constant, so constant speed. That's not happening. It's slowing down, stopping, then again speeding up, again slowing down, stopping. So this cannot be so sharp here. It has to be somewhat smoother. What kind of function has that? Some students will say, oh, maybe it's a sine or cosine function would be better. There it is. Okay, smoother, smooth transition from one direction to the other, smooth transition. That's what it physically looks like, okay? So maybe this is one of the possible solutions, okay? Sine or cosine. It's the same thing. Sine and cosine is just shifted by 90 degrees. That's it. You could derive the formula in details and tell, okay, yeah, sine function. Also look at it this way. The second derivative happens to be the same as the first derivative of the original function, with just a minus sign and some constant. Sine function, sine, the first derivative is cosine, second derivative is minus sine, right? So both sides would match. This side equals that side. Okay, so yes, looks like sine is a possible solution. Sine or cosine is the same thing. So a general solution you could derive, you could show that this general solution would satisfy this one, okay? X equals a, some kind of constant, then sine, and then a function of time. Sine t, if you put just sine of time, then there will be some mismatch with the period, so you got to include this part. Okay, this part somehow turns out to be there. Because if you take the second derivative of this one, twice this part will come out. So you can explain the details of mathematics. You are all professors and lecturers. I'm not going to explain all the details, but you have to slow down at this point and explain the details. Why this? Okay? So this is called a phase angle. Okay, that doesn't make a difference. It just shifts this by a slight amount. Okay? And remember, sine, all these things inside is in radian. That's very important. Quite often you have to go back to some very basic things where students go wrong. Quite often they plug in degrees and it doesn't work. Sir, I'm getting something wrong. Well, that's because they forgot that these things are in radian, these angles, okay? Degrees are just for our convenience. Okay, there's a constant here with which the time is multiplied. That constant turns out to be the square root of this term, okay? Without the minus sign, okay? This is very important. K is this stiffness, and this is the mass, and that's called circular frequency. Explained to them later on. And this is the frequency, the circular frequency divided by 2 pi. What that simply means, in 1 second, how many radians? Suppose it's similar to going around and around an angle. In one second, how many cycles it will make is this one, and how many radians it will make is that omega. Okay, how many radians? Time period is the inverse of this one. If I say in 1 second it makes 10 cycles. Cycle? Okay, I'll explain the cycle right away. From here, if it's starting from here, going up, down, and coming back to that point, that's called 1 cycle. Or if you start from here, if you count from here, from top, it goes down all the way, comes back to the top. That part is called 1 cycle. Okay, so the time taken to complete 1 cycle happens to be 1 over frequency. Okay, why? It's obvious. If it's making 10 cycles in a second, then the frequency is 110 cycles per second. Okay, cycles per second is also called hertz. So remember, these are very simple relations. This omega is radians per second, frequency is cycles per second, because 2 pi radian makes 1 cycle. All right, but let them absorb these things. Tell them, you think about it and write a couple of lines about it, or explain to each other, the students. Okay, because these small problems here, plugging in F instead of W, can throw the result away completely. Okay, so let them figure that out. So what did we do? We took an assumption that it should be probably sinusoidal. This looks right. And then we also mathematically express that in general solution. Now, general solution involves two unknowns. This phi or phi, which is phase angle. Phi is the Greek name for this letter. Many people call it phi. It doesn't matter. And there is a constant a. The sign multiplied by a, it just remains the same thing, just becomes larger or smaller. Okay, just this part changes. So that's also going to satisfy this. Are you sure it's going to satisfy? They will not believe it unless you actually substitute it. Check by substituting it in this differential equation and make sure that it's satisfied. It's not, then the solution is wrong. Okay, so how do you do that? Very simple. How would you check this? You take that, you're assuming that's the solution, take the second derivative, put it on the left side, and this side you plug in this x value and see both sides are equal. Let's check. I'm going to take second derivative of this one, a. Okay, sine derivative is going to be a cosine, and again next derivative is going to minus sine, right? So minus sine, that part. But when you take the derivative, this omega comes out. So first time omega came out, second time it became omega squared, and omega squared is k over m. So left side is complete. Okay, right side, k over minus k over m times x. X comes from here, and they're exactly the same. So this form of solution satisfies this equation. That's verified. Okay, now these are knowns a and phi or phi. That will come from specific problem. How much you have stretched, it will depend on that. Okay, it will depend on initial conditions. Those are called initial conditions. Actually, initial condition could be at any given time. If you know two things, you should be able to solve these two variables. Okay, so usually the conditions could be something like this. Let's say one particular condition is this, now there is this, now there's this. Let's look at this one. At time equals 0. Let's say I stretch it and say that's my time equals 0 when I release it. Okay, from there I want to check the motion. Okay, time equals 0, x equals a. It could be 5 centimeter or whatever. It's a. Let's say it's a, some variable. And velocity was 0. At that point it was stationary. Later it started picking up the velocity, right? Velocity was 0 at that point. From this condition, initial condition, you should be able to figure out these equations here. Okay, a will come out to be a. That's fine. Now this phi will depend on this v. How would you get v? Well, first derivative. That's it. You know the displacement? Do not give them the answer. Ask them, how would you get the velocity? Somebody will say yes. It's always appreciate their answers. Okay. V equals x dot, which is dx over dt, a cosine omega t phi plus phi, and 1 omega comes out, a omega. That's what it is. Okay, so they plug in the value. V equals 0 at t equals 0, so this part becomes 0, cosine phi. So a and w cannot be zeros. Then it's not moving at all. Okay. So this cosine phi must be 0. Cosine of what angle gives 0? 90 degrees, right? Cosine 90 degrees is 0. So that means phi equals 90 degrees over, or pi over 2, half pi. Okay, so they found out, and this a turns out to be a exactly. Okay, so that's how it is. Let them do this part. Let's say you do this part, solve for them, and say, okay, these two different conditions, these are 3 different problems. Same system, 3 different initial conditions, so 3 different solutions. This is the general solution that will be valid for any system of this kind. Okay, let them find out A and phi based on this. How about this second one? Look at this. What I'm saying is I'm not stretching it. I'm slowly releasing it till the point it stops, and that's my reference. Gravity and other things I ignored in this because I'm considering the neutral position where it stops. Okay, all right. But I'm applying initial velocity. What that means is very difficult to apply initial velocity instantly. But let's assume somehow I hit with a hammer very quickly and it gets a velocity. That's it. Okay, some velocity. How do you find amplitude, etc., based on that? Phi and amplitude. I introduced the term amplitude here. I didn't explain what it is, right? It's very important. The students are going to catch you. So what's amplitude? Okay. It's not amplitude, it's amplitude, okay? So this is the zero position. From there, what's the maximum value it goes up to, okay? Maximum or minimum, the magnitude of that is called amplitude, which turns out to be this A. Why? Why is it maximum? Look, sine can only vary between -1 and +1. So this X can have maximum value of -A and +A, okay? That's the reason. Okay, let them think about it. Don't tell them everything. I'm telling you because just to give you some hints. All right. The third one, I do pull it, stretch it by some amplitude, also apply some velocity, okay, initial velocity. And then also let's ask them to find out maximum velocity in this case. In this case, it's going to be larger than A because it's already pulled by A. Then a velocity is applied. If it's in the same direction downwards, the amplitude is going to be higher. Let them figure that out, okay? All right, let them do some work. Let them do some thinking. Just listening to you is not going to help much. It may clarify some problems, but that's it. Let's check with the real numerical values for the mass spring experiment. If you have brought the hardware, please measure that and ask them to solve exactly the same problem with the real numbers. How much is the mass? How much is the spring constant? All that. Okay, they'll be excited. Just A, B, C, D, sine, cosine, etc. Not enough. In engineering, you need the real values with correct unit, correct sign. Okay, it's really important. It's not just theory, just algebra. It's not that. It's real numbers. Okay. If you work for industries, you know how important it is. People say this is only a plus minus mistake or decimal point mistake. No, that can cause catastrophe. Okay, take it seriously. You're teaching engineering students. You're creating future engineers. How does T depend on amplitude A and mass M and stiffness? Wow. T, time period. Does it depend? Time period is relation function, and this is related to omega. Omega is related to K over M. They should be able to figure out amplitude, mass, time period depends on amplitude, mass, and stiffness or not. It doesn't depend on amplitude. Do that experiment right away. Measure how many timing with the video and stretch it even more and do the same thing. You'll be surprised that it doesn't depend. The time period, how much time it takes to complete one cycle doesn't depend on the amplitude. It depends only on mass and stiffness. If it's stiffer, it vibrates faster. If it's softer spring, it vibrates slower. Heavy mass, slower. The denominator that they should get somehow by thinking. Here's the numerical example of the experiment I'm doing. K, stiffness is given as this. Mass is, I'm using Excel. You can use Excel or Mathematica. Show them the calculation or assign as homework. They should be able to do numerical experiment with it, okay? All right. Stiffness is given. Mass is 100 grams, 0.1 kilograms. Omega is square root of K over M, turns out to be 12.157. Remember, this is radian per second, not degrees, okay? It's angular frequency. Frequency turns out to be omega divided by 2 pi. I've chosen the numbers in such a way that it turns out to be 2 hertz. Hertz is same as cycles per second. Time period is the inverse of that, half a second. That means it takes only half a second to make one cycle, right? So it makes 2 cycles per second. So that always double check and think if the numbers are matching with whatever is given. Okay, always verify. Because quite often just from a slight mistake in typing in the formula can make the results go off completely. All right, now the amplitude, I'm stretching it by 5 centimeters, so that's 0.5 meter. Okay, now using these initial conditions, I have given in one problem, at time equals 0, x, they put in this value of x formula, they put in and calculate phi. They can calculate from the initial condition, it turns out 1.50. What is that number? It's in radian. It's pi over 2, 90 degrees. Why is it that? They should think about it. Because I give initial condition 5 centimeter. So it has to start with 5 centimeter. Okay, because I'm going to plot it. Okay, it wasn't 0. X was not 0. So it turns out to be this thing. It's same as sine something plus pi over 2 is cosine, right? Okay. Now time, they take some discrete times at different times. What will be the formula they have to type in? Formula for displacement, and these are the things. Then they plot it. The time, and there is displacement versus time. It looks like a sinusoidal, right? Sinusoid. So they can probably stretch it down to like 50, 60 numbers and plot it nicely, smooth curve. Now they should study. Oh, look at that. One cycle gets, firstly, it starts with 5 centimeter, which is correct because it shouldn't be 0. So it's actually a cosine curve or sine omega t plus this pi over 2, turns out. Okay. All right. Then it goes through down and up, down and up. Actually, it's reverse. I have chosen x down that way. So it's in plotting. This part is down, this part is up. All right. And this part is called amplitude. It turns out to be all of them the same. Maximum value is 5 centimeter. That's fine. Good. Frequency, in 1 second, it makes 1 cycle, 2 cycles. Matches there, 2 cycles. Time period, how much time does it take to make 1 cycle? Here, half a second. Perfect. Let them do some experiment by varying these things. Okay? K and M and A. Maybe even initial condition that will change the solution, particular solution. Homework. Assign some homework to them. This is really important. If the mass is released from a position where the spring was unstretched, this is going to be difficult, right? Spring is there, and that's where the spring is hanging. And then I put the mass, and I slowly released it, right? Then I stretched it. What if I did not slowly release it? Just hang the mass there, keep the spring unstretched, and just drop it. Leave the hand. How's the motion going to be? It's going to drop because of its weight, but the spring is trying to pull it back, so it will hang here, right? Ask them to solve that problem. Let them think the details, okay? Plot it. What would be the amplitude in that case? Okay, there's potential energy of this mass, and then spring had no potential energy. Then when you drop it, it picks up some motion, wants to drop. The entire energy, if it dropped, say maximum dropped to here, all that energy of the mass gets converted into energy of the spring, half kx squared. Okay, let them think about that. Homework 2, explain why for a simple pendulum, the time period doesn't depend on the mass of the bob. Okay, it doesn't depend. But here you saw time period, t or frequency and omega, everything depends on the mass and the stiffness. Why is the difference? They should explain in writing. Think. Do some research and answer the following in a few lines. While studying engineering vibrations, why do we study mass spring system? Do you see mass spring systems all around you? We showed you bridge, we showed you airplanes, and maybe some buildings also you could show, vibrating sea. These are not mass spring systems. Why are we studying such a fictitious system or very rare system that you see only in the labs? Let them think. Do you know the answer? Very complex systems can be modeled as simple as mass spring systems, combination of many masses and many springs. So once you study this details, understand everything about it, you can extend that to study vibration of very complicated machines, structures, etc. Okay. All right. With vibration, what else can you add to your class, this lecture? How would you find K, spring constant? Ask these interesting questions. Always ask some interesting questions. It can get very boring if, to listen to your monologues. So you have to ask them questions to keep them awake and alert. Okay, I've said that many times in my previous lectures. How would you find? Let them think about it. Okay, you got the spring and the mass. If you know the mass, if you said it's 100 grams or 200 grams or whatever, you take a ruler next to the spring, put it there, and suppose the spring is hanging there. When you hang the mass, very gradually see how much it displaces. So the weight of the mass would be balanced by the spring. Spring got stretched. The force of the spring is going to be equal to the weight mg of this mass that's hanging there. Okay, and you know the stretch. So mg is the force. Spring force is equal to that, and came to an equilibrium position, divided by the displacement that you measured. That's going to be spring stiffness. Okay, it's that simple. But they should be able to answer that. Think about it. They'll feel so good that they got it right. Okay, make them feel good that they're understanding, applying, coming up with answers. Really important. Okay, don't spoon feed them. Let them think. You can help them a little bit if they do not get the answer right. Derive velocity and acceleration formulas, function of time. I already did that, but let them do it too. Plot velocity and acceleration on the displacement. In that same Excel chart, ask them to write the formula for velocity and acceleration. Put those things in the next columns. Ask them to calculate, plot over that, and see the relation between them. Okay, velocity, and they'll be amazed that why is there shifting? There is a shift where the velocity is maximum, where the displacement is maximum, velocity is 0. Yes, because it came to an end. Okay, maximum displacement, there it stopped, and it's reversing. There's a shift. They should understand these things. Okay, so sine becomes cosine when they get the velocity. They'll be amazed at these simple things. Oh, mathematics does work. All right, let them plot that. Of course, the magnitudes of these things are not going to be the same. Okay, maximum values are going to be different, velocity, acceleration, and displacement. Let them think about and absorb all that in their mind. Observe the plots and find the minimum and maximum of these things and draw the conclusions. Okay, when it reaches the maximum displacement, velocity becomes 0, but acceleration is also maximum. Okay, good. What's the phase difference between v, x, v, and a? Okay, just looking at the maximum, they can figure out the maximum of this, minimum of this, or 0 of this. There's a maximum of this. There's 90 degrees phase difference, another 90 degrees, and so this one, 180 degrees, whatever. Let them write that down. What is phase? Explain this phase. I have been talking about this. Explain what is phase. That phi was the phase. Any sine curve, if you shift it by some angle, okay, it remains the sine curve. It's shifted by that. That shift is called phase. Okay, that phi or phi. Okay, sine and cosine, for example, they're exactly the same curve, but shifted by a phase of 90 degrees. They should know these simple things in their mind. Okay, how does it depend on initial condition? So these three problems, if they see and they observe that first problem that they solved, numerical problem, second problem, that particular solution they found, yes, one has a phase difference from the other. They should know. Just the time part is shifted. Okay. In what other forms can the general solutions be written? As I said, sine and cosine are basically same function. They should think about that and say, okay, I could write the same thing as cosine. Only thing that will change is that phi. In one case, it may be 0. If I wrote instead of sine, if I wrote cosine, that particular problem, it may turn out to be 0. Okay, now that phi, whatever. There may be other possible too. If I can write sine as a solution, cosine as a solution, then the combination, linear combination, would be another solution. So I could write the same solution as a sine omega t plus b cosine omega t. That would be a solution to linear combination. They should think about these things. Mathematics and physics, all these things should make sense together to represent this real system. What are the potential energy, kinetic energy, and total energy of the system? Of course, something is moving, that's got kinetic energy, and sometimes stops, so entire energy gets transferred into potential energy of the spring. They should be able to find out. Energy is being conserved, let's assume. It's moving for a long time, so it's almost conserved. Not being lost. Energy is always conserved, but it's not being lost. Now, lost into the surrounding, let's say. No damping. Now, energy of this, suppose it's going down, when it stops, all that energy, kinetic energy, has been transferred into potential energy of the spring, half kx squared, because it's a triangular shape. Okay, if you plot force versus displacement, it's linear spring, it's triangle, so the area of the triangle will get the potential energy of the spring, that's half kx squared, they know that. Okay, from physics. Now, that should match the maximum energy, kinetic energy it had. So let them figure that out. Okay, this energy transfers, the total energy, how much is the total energy? And these concepts will be useful. How does the total energy vary with amplitude and frequency? This is really important. Any vibration, they should know the relation between the total energy of the system and the amplitude and frequency. Higher the frequency, higher is the energy, higher the amplitude. But how? Not linear. They should figure that out. Okay. Let them calculate the energy and figure out how does it depend on amplitude and frequency using simple algebra and formulas for energy. Think if we can derive the formula from energy conservation. I think it's possible. Just let them think about it. Not starting with Newton's laws of motion, the second order differential equation. Can we derive somehow using energy conservation? I think it's possible. Okay, there are energy methods. What if they don't have to go into the details because this method is going to be taught much later maybe. What if you have two masses connected in a series? Okay, one spring, and then a mass, then another spring, another mass, two masses. Okay, let them think about these things. What will happen if I stretch this move? Yeah, this will move like this will move like this. What if it moves like this? There's some opposite, maybe both moving the same direction. What will happen? Okay, so let them imagine and think about the physical system. How do you formulate the problem and solve them? Well, they should be able to say, if I can solve for one, maybe I have to write make the free body diagram, write the equations for two. I'm getting two different differential equations. So okay, the solution is going to be complicated, but it's possible. Introduce degrees of freedom and modes, etc. These things you have to introduce to them the concepts. Okay, if two things are moving, it could be moving like this. Okay, and it could be moving like this. So there are two different modes, got two independent ways of moving. Okay, they may be related, but one affects the other. But it could move this way, and that one could move that way. So they are independent in some way. So those are degrees of freedom, modes. If I had allowed it to swing like that, that would be another degree of freedom. So introduce slowly as a concept. Okay, later on you can always define them. Concepts are much more important than the definition. Definitions must be precise, that's fine, but sometimes difficult to get the concept. First explain the concept, then introduce the definition. That's my style. Vibrations and sound waves are related. If something is vibrating, if there's medium, let's say surrounding it, water or air, that starts vibrating. Those particles, they get compressed and decompressed. Okay, compressed and expanded. So that creates waves, and that's the wave that comes to our ear and we hear the sound. Okay, so they are related. Also, if there's some, let's say a beam or some metal, and if this part is vibrating, that vibration as wave gets transmitted throughout. That's also sound. Okay, so they are related. Similar studies are used in electrical engineering too. What does that mean? In electrical engineering, especially in AC, sometimes the equations are exactly same. Second order differential equation, exactly same as the equation you saw earlier in vibration, mechanical vibrations. The analysis and all that is going to be very similar. Okay, so they should not think I'm studying only mechanical engineering. Suppose some electrical engineers studying this should not think that this is useless for them. No, they are all related. Okay, they should know a little bit about everything. Good. That's all for now. I've given you enough lectures. In the next lecture, we're going to talk about other implementations, more complex problems, etc., and conclude. Thank you very much.